presentations at conferences recently about cracking passwords in the cloud, and they all kind of start the same way. You go to Amazon EC2 and you start up a whole bunch of computers, and you log in, and at that point, you're not operating at the scale of the cloud. You're going too slow. What we want to do is this. So this is a dashboard, and each square is a unit of work, and each yellow one is one that's in progress. So I have about 800 cores chewing their way through all of this work that I have to do. And that's what this talk is about. And what we're going to do is we're going to use a program called BOINC to put any application and run it on hundreds or even thousands of machines. And setting up any type of server is a bit of a dry topic. So I'm going to put in two examples, factoring our SATs, so 512-bit SSL Certificates or PGP private keys, and cracking password hashes. But more so is you guys are doing interesting stuff, so I want to inspire you to think about how BOINC can help you, and if your problem will run in BOINC, and if so, how you can get it going. What's really important is everything is online right now. I put it up last night, so you can go to GitHub if you're online right now and get the slides, and the slides with all reference links inside next to them, as well as the scripts and the sample templates. So I try to give you everything that you need to get up and going right away. So let's talk about BOINC. Did anyone here run SETI Home back in the day? Okay, we got one enthusiastic guy, a couple people. Okay, so SETI Home was an awesome idea from a university in California. They listened to space, listening for noise from the electromagnetic spectrum. So we humans emit lots of signals, television, radio signals out into space. And the idea was, if there was some sort of alien civilization, they would also be broadcasting. Not necessarily to us, just their own stuff. And we wouldn't understand it, but it wouldn't be random noise. But seeing as something is random takes a lot of CPU power. So they got volunteers. And you would run their program on your computer at night or whatever, and it would see if the signal was random. And this was lightning in a bottle. It was a fantastic idea, and people got really enthusiastic. So they took the idea of volunteer computing, and they turned it into a program called BOINC. And now anyone can create a project for anything and ask for volunteers to run the software. Now, us in this room are generally not going to be asking for volunteers because we're very secretive, we're security researchers. So we're going to kind of run it in Amazon, but we're going to use the BOINC software to manage all of the work. So why would you use BOINC and not something else? BOINC has been around for a long time. I didn't write it. If I wrote something for a conference to give a talk, it would be useless. It wouldn't be maintained. But BOINC has a very large community around it, and lots and lots of features. So it runs on every operating system, not just Mac, Linux, and Windows, but also HP UX, Solaris, and all of the BSDs. It handles client problems. So if the client crashes, if a program crashes, if the network goes down, all that is taken care of. It can run any type of program, including GPUs. If it didn't run GPU-powered programs, you wouldn't, even want to listen to me, because if you're not using GPUs, you're not, cool anymore. So, about how you do this, you set up the server, which is pretty much just editing an XML file, and then we're all paranoid, so you lock it down. And then, if you're doing this, you have some idea of what you want to work on. Let's say it's fuzzing. You want to fuzz a program and you have, say, 50 files. So you're going to figure out how to distribute that work. 50 files, one file on each computer, very straightforward. You set up your application that you want to do the fuzzing. So whether that's Peach or something else. And then, because we're probably going to work in Amazon EC2, you're going to set up a client image in Amazon that will, on startup, connect to your server and just ask for work. So you're not putting Peach or your program on there. All you're putting is the BOINC client software, which is what runs on every single operating system. And then you create your work unit, so that will be each file that you want to fuzz, and you're good to go. And none of this is particularly difficult. Setting up the application can take a little bit of trial and error. Hopefully, with the samples and the materials that I released, you'll have a much easier time with that than I did. So, I have to give this disclaimer. BOINC tries to be as secure as it can. Not entirely. I wouldn't tell you where my BOINC server is. Let's put it that way. So if you want to run BOINC, just keep that in mind. Or if you're looking for something interesting to audit and you like the idea of taking over a server that can control hundreds of other computers, go take a look at BOINC, I guess. So the last thing I need to explain before we get into the examples is this life cycle of a unit of work. It can be a little bit confusing, and the terminology is very specific. So you're going to create these BOINC work units. That's each file that you want to fuzz. And you're going to load them into the server. And from that, the server is going to create what's called a result. The client is going to connect to the server and be assigned a result. So let's go back to the dashboard. You can see those tiny little red squares. That's a result that failed. So something went wrong on the client. It crashed, or something went wrong. So we still want to fuzz that file. We still want the answer. So BOINC will create another result from that work unit and send it to another client where hopefully it'll succeed, and then we can get the answer. We move on to validation and assimilation. These can actually be really complicated, but for us, we keep it very simple. Validation is making sure that the client sends something that's sane, that makes sense. So as long as it didn't crash and all of the output files that we're expecting are there, we're going to consider it valid. Assimilation is doing something with that answer. So the most common things to do would be to put it into a database or put it somewhere on the file system. And the sample assimilator included with BOINC just puts it into a folder. And then finally, the work unit is marked as completed. So now let's get into factoring. So I'm going to talk about semi-primes a lot. So just to refresh you guys, if you have two primes, the product is a semi-prime. So 5 and 3 are prime, 15 is a semi-prime. We're going to be working with much larger numbers. A 512-bit semi-prime is about 155 digits long. So in 1999, a 512-bit semi-prime was factored for the first time publicly. We don't know what world governments are up to or what the capabilities of. And in 2004, the open source tools that we're going to use for factoring began development. And in 2009, things got really interesting. So I don't know if any of you remember this, but one of the cool things about the internet is any form of nerdery or geekery has its own community. So there's a community of people who write their own operating systems for these calculators. And they load them on using something similar to a tethered jailbreak for an iPhone. And the company that makes these calculators, Texas Instruments, or TI, has a signing key. And what one guy did was he took a look at this signing key and he saw that it was 512-bit. And he thought that he could break it. And he did. It took him about 5 months, but he broke it. And then Texas Instruments issued takedown notices, and the EFF got involved. The keys were posted on WikiLeaks, back when WikiLeaks actually had a wiki. And it was really cool. And of course, some guy came up and said, hey, I can charge a bunch of money for this, so he created a service. And there were about 15 signing keys. And it took one guy 5 months to do the first one. It took the community 2 months to do the next 14. And then a little bit after that, a 768-bit semi-prime was factored for the first time publicly. It took a really long time. So if you're thinking about doing this to break 1024-bit keys, it's a little bit out of reach still. Sorry. So how do you factor? Breaking RSA, so RSA used in SSL or public key cryptography, the most straightforward way to break it is to factor the public modulus, the public semi-prime. And the easiest way to think about factoring is it divisible by 2? 3, 5, 7, 11, 13. You just try each prime. That's really slow. There are a couple of other algorithms, Pollard Row, ECM, but the one that we're going to use is the general number field seed. Now, I felt bad saying the general number field seed and waving my hand, so I'm going to show you a little bit about what it is, but this isn't that important. So, especially the stuff on the right. So, if you don't want to read that, you don't have to. So, polynomial selection, you're going to find equations, and these occur randomly, and they have a quality associated with them. And certain polynomials are better quality or worse quality. But you're going to look for these. And then, when you found a good polynomial, you're going to sieve. And you need to find millions of pairs of numbers that fit into these polynomials. This is what takes the longest time ordinarily. It takes about 3 months to sieve on one computer. And then there's the combine, and if you thought the first two was complicated, this is just fucking magic. So you build this massive matrix, and then you solve it using linear algebra and this really complicated algorithm called Lankos. And that takes about a PhD in math to begin to understand. Fortunately, we don't have to. We can just run the program. And that's the gating factor for us. That's the slowest part for us. You cannot break RSA faster than the combine because the linear algebra does not scale to multiple computers. And it takes about a day for a 512-bit number. So let's talk about the first step and put it into BOINC. Polynomial selection. Like I said, polynomials occur randomly. We have to find them. This was the result for one semi-prime. And I found a bunch of polynomials over there and a few over there. But for you, it'll look completely different. So how do we actually do this? There's a program called MSIEV. And it's fantastic. It is beautiful C code. It does all the factoring algorithms. It's actively developed and maintained. The author is a really nice guy. There's a community of people who use it. And we're going to use it for polynomial selection and the combine. There's a slightly better program that's much older for sieving, but it's not maintained at all. And I'm not going to say that Jason P. is Batman, but I will say they've never been seen in the same place at the same time. So let's put MSIEV into BOINC. It's really easy. Like I said, MSIEV is open source, written in C. We're going to replace all the calls to fopen with BOINC fopen. We're going to call BOINC init in the beginning, and BOINC finish in the end with the return value. And when we compile, we link it with the BOINC libraries. If you want to do more, you can. Like if you're writing a program from the ground up, you can put in checkpointing. So if a client shuts down in the middle, it can restart in the same spot. But for us, we don't need to do any of that other stuff. And this is what it looks like. So I find main, the old main function, right down there, and I just rename it to sieve main. And then I write my own main function. And it's going to call my BOINC start, the old main function, which is sieve main, take the return value, and pass it to BOINC finish. And my BOINC start just builds up argc and argv, the command line parameters. So you can see -i, -nf, -np, and there's that stuff at the top, BOINC resolve file name. Unfortunately, that's the other thing that I didn't mention in this slide. So if you have a program that writes out a log file, let's call it log file, and you run 2 instances of that program, they're going to step on each other. They'll both try and open the file. They'll both try and write to it. You'll have problems. BOINC needs to solve this, and here's how they did it. You write a template. Here's the input template, and you can see the name there, RSA key. RSA key is the logical name. That's what the program expects. the physical name on disk will look different. It'll look something like work unit 1234501. So you're going to write an input template, and there's these other options for sticky and no delete, and all that's explained in the material, so I'm not going to go into it on stage. And you're also going to write an output template. So there's a logical name of log file. And again, more options. The output template is what BOINC expects your program to write out and what it's going to send back to the server. So we've got MCs running in BOINC. Here's how we split up the work. Like I said, we search for polynomials at random. So we take this range from 0 to 10,000 and just split it into chunks. And we send each chunk to a different computer. And we're going to get all the results back, and then we do sieving. Sieving is the very slow part, and we're going to operate over a range as well. That range is called Q. I don't know why. It just is. We're going to sieve from about 12.5 million till 70 million, about when we're done. And this graph shows the number of relations that we get for each Q value. So at Q of 12.5 million, we get about 1.5 relations. At 60 million, we get 1 relation. At 60 million and 1, we get another 1 relation. And we need to get about 60 million of these relations. We're going to use a program called GGNFS. And running it in BOINC is about the same way. We rename main, and we build up argc and argb, and we're good to go. I have to give credit where credit is due. This idea of patching main and running factoring in BOINC was first done by the calculator guys, United TI. So I took their ideas and their work and I built it up a bit. So again, we're going to take that range that we need to work in, split it into chunks, send each chunk to a different computer. Like I said, this takes about 3 months, so we're going to use a lot of computers for this stage. About 400, 450 if we want it done in an hour. So that's 3 months of work in 1 hour. It's pretty cool. And then we do the combine. Like I said, this takes about a day. So 24 hours later, we're going to get the results. And this runs on a single computer. In May of this year, I think it was, the country Syria started intercepting Facebook traffic. They used a 512-bit self-signed cert. So really, really obvious. They weren't nearly as smart as the Iranian hackers. I looked at this and I was like, hey, I bet I can break that. And I did. They started intercepting on Tuesday. I started working on it on Thursday. I had the result on Saturday. And with these primes, you can impersonate Syria, impersonating Facebook. And 512-bit keys do still come up. If you're a pen tester, you may see it on an engagement, which is really cool because you can hand the client their private key. And there's actually a new service called Cloaklet. They were kind of, I'm not quite sure the word, not harassed, but embarrassed a little bit when people who actually knew security took a look at their security. They built themselves as some sort of like anonymity system, kind of like Tor, and they did like encrypted email and stuff. But they didn't really know what they were doing. They did everything in ECB mode. They weren't using secure random. And the subject of your email was encrypted with a 512-bit key. So I had actually planned to grab their public key and factor it on stage for everybody, but I couldn't even create an account because it required Java. Remember, they built themselves as secure. It required Java. So if you want practice factoring, go take a look at Korelogic. I had promised in my abstract that I was going to talk about some of the details that I had found from the general number field sieve and some interesting tricks. I had to cut it out. It was too off topic, the talk was too long. But I put everything in its own slide deck, and that's on GitHub. So you can, if you're interested in the math part of stuff, you can go take a look. There's tons and tons of graphs. Everyone loves graphs. So far, we've run open source programs in BOINC, and we've factored RSA. Let's talk about running closed source applications, doing GPU applications, and doing password cracking. So, sieving in the general number field sieve is what's called embarrassingly parallel. It's a computer science term. And what it means is that something should be so simple to run on multiple computers that it's embarrassing. But there's two sides of this coin. There's embarrassingly parallel in theory and in practice. Something that's embarrassingly parallel in theory should run on lots of computers, so sieving and cracking. But that doesn't mean it's embarrassingly parallel in practice. Because if you have to write your own code, then you have to do work, and that's not embarrassingly parallel. So sieving was embarrassingly parallel in practice. The programs were there. For cracking passwords, not so much. So the two biggest crackers are John the Ripper and Hashcat. John the Ripper is open source, and there's several MPI patches. So they run on multiple cores in a computer. If you have a 64-core machine, you're good. If you have 64 one-core machines, you're kind of screwed. So there's something called mode external. Mode external will split the work between any number of computers. But all it does is skip passwords. So the first computer will take the first, the second, third, fourth, fifth. This has a lot of overhead when you run it on 400 computers. And you can't add computers in. Hashcat is closed source. It's very, very fast, but you can't really modify it in any way. And I thought, I have a whiteboard. I can solve this problem. So I thought about how you do password cracking. And this is kind of how it works. If you can imagine this line is all the possible passwords that a user could choose, you're going to do a brute force attack. And then you're going to use a word list. And another one. And right about here is where you stop caring and start watching TV. So you use another word list, and then you use some foreign word lists, because everybody has passwords in Finnish, right? And then you just start throwing crap at it. And this can work for a fast hash function, but not for a slow one. You can't do Blowfish or Unix MD5 with that technique. So here's what I came up with. Here's how I was going to distribute the work. First, I was going to run John single mode. And then I did a 1-hour brute force. It's a phased approach. So I could say that it was only going to be 1 hour because I did a whole lot of measuring. This line shows my accuracy of my measurements, and it's pretty close to 100. So I measured how long each hash function would take, and how long any individual work unit would take to process. And here's why. If I have a big word list, and I don't know how long it will take, and I send it to a client, and I get the results back in 3 hours, that's 3 hours that I was doing playing games. So if I know it's going to take 3 hours, I can split it into 3 word lists that will each take 1 hour. Send it to 3 computers, get the results back much faster. And that's what my script does. It would take a word list, take the hash function, and chunk it up so each client would just get a small piece, and I'd get the results much, much faster. So I'd run it with word lists, and then I would use word list rules and then Markovs. So if you've never heard of a Markov generator, the easiest way to explain it is Italian surnames. So think of Italian surnames. Berlusconi, Trattoria, Luciano. They're very easy to create in your head. If I told you the letter L, you would think what follows it. Probably another L or a vowel. That's what Markov does. It takes an input dictionary and produces more words that look like it. So when I run a Markov generator with a German word list, I get German-looking words. When I run it with a French word list, I get words that end in Z. So I was very careful with these word lists. They didn't overlap, even with mangling rules. So I was really meticulous about this. And I set up this entire system that would go through, and I thought this was going to crack all of the passwords. So now let's put the programs into BOINC. So John the Ripper goes into BOINC pretty easily. It was a little tricky. The patches are in the material, so you don't have to do the work that I did. We just rewrite main like we did before, and we build up the command line arguments. I'm going to take this opportunity to talk about application versioning. What happens when you need to update an application? Either a new version of BOINC comes out, or you made a mistake when you were patching it. It's basically, there's a specific file name pattern that BOINC uses. So for msieve, the first part is the name of the program, so msieve, and then the version, major.minor, there's only 2 decimal places, and then the platform. So this runs on Linux. You can have all other platforms, Linux x64, Mac, Windows 64. If you need to, you can have a subfolder with resource files, like a database or something. And unfortunately, you can't have subfolders under there. It doesn't quite work. I have a patch to BOINC that will let that work. It's a hack, but it is all right. There's other ways to do that, though. Now, what about Hashcat? Hashcat is closed source, and it's a GPU application. BOINC has what's called the wrapper app. And the wrapper app reads job.xml and will run each task that you define in it. So here we define Hashcat. And we can wire up standard in, standard out, standard error. And there's other options too. You can run a program as a daemon. So it'll run in the background while all the other applications talk to it. So if you were crazy, you could try fuzzing like Apache or Nginx with this. And if that's not enough, there's something called genwrapper, which is basically bash. You write a bash script with loops and conditionals, and the tools that you're used to on Unix, cat, grep, so on and so forth. Now what about GPUs? So it's very similar to the naming pattern. We just tack on another piece, underscore underscore CUDA. That's called an app plan. And there's a bunch of different app plans. So MT is multi-threaded. And there's specific GPU targets. Only run this on a computer that has a Fermi graphics card. And there's something called NCI, non-CPU intensive. So if you wanted to do distributed Nmap scans, if you wanted to scan the internet, you could distribute that using BOINC. You can even run things inside of a virtual machine. That's very experimental, but if you wanted to, you could potentially fuzz VirtualBox from the inside using BOINC. So we've got John the Ripper, and we've got Hashcat running in BOINC, and we know how we're going to distribute the work. How do we measure this? In 2010, a company called Korelogic ran a contest, and this year as well, at Defcon, called Crack Me If You Can. This graph shows all the participants, the number of cracks they had over time. I didn't participate in the contest, but I could take the list of hashes and compare myself. So I didn't use any of the answers or any of the word lists they released. I just ran it myself, and I would compare myself. And like I said, I had a whiteboard. I was invincible. I was God. I was going to win this hands down. Not quite so much. It didn't work really nearly as well as I had hoped. You can see that not only did I not crack as many passwords as the better teams, I stopped in the middle. This entire idea was I wanted to do password cracking hands off. I wanted to load up all of this work into BOINC, let my army of machines run it, and then go to the bar. And that was the wrong approach. This breaks down my failure into more graphs. So in the bottom right, you can see that most of the hashes were NTLM. And in the upper right, you can see that purple bar. Those are passwords I didn't crack that someone else did. So NTLM is where I really failed. But NTLM is a very fast hash function. What the best teams did was something called iterative cracking. They would crack a whole bunch of passwords, take a look at them, look at the patterns, run programs to analyze them, and then crack more passwords using those initial cracked passwords. And that's exactly what I didn't want to do. I actually did not want to sit at my computer and stare at hashes. I wanted to be out enjoying Vegas. So if you wanted to do password cracking in BOINC, I have the way to distribute the work, but you're still going to need to pay attention and actually look at the results and create more work every so often. You could try automating it more if you wanted to, but you definitely need to have this feedback and creating new mangling rules. So let's bring it back to BOINC and then wrap up. So if you want to set up BOINC, you're going to set up a server, lock it down, and then you're going to take you're probably going to run this in EC2, so you're going to set up a client image and then set up an application. So you're going to pass the source or write the job.xml, and then write the input and output templates. And that's the trial and error part. You can see it kind of loops back as you need to try again and again. And then you're going to run update versions, which is the loads your application into BOINC, see if it works, and if it does, then you can go off and automate the client image. And then, I don't know, go fuzz, find a bug, sell it to Grok for 50K, retire in the crime island. So, I should mention what the alternatives to BOINC are. If you're only interested in password cracking, there's a few things. There's been a whole bunch of browser-based password crackers. These are all very cute. They run in JavaScript, they're not very fast, and it's more just of an interesting experiment. There's a project called Durandal. Durandal is basically BOINC for password cracking. So it's just started. If you're interested, by all means, take a look. Rick Redman from Korelogic does a lot of password cracking. He runs a Crack If You Can, which posts daily password dumps from Pastebin. If you're at all interested in password cracking, you should follow that Twitter account. He's got his personal tool. He demoed it at SkyTalks at Defcon. If you're intrigued, shoot him an email, encourage him to open it up. He's not quite sure what he wants to do with it. Otherwise, there's Amazon Elastic Beanstalk. That only runs Java, so it'll distribute work and stuff. But we were interested in running things quickly, and it's Java only, so it doesn't really mesh. There's Amazon SQS. All that is a messaging queue. So you're going to load all your work into it, but then you have to write your own program that'll look at the queue, do some work, and then do something with the results. So I don't really consider it a big alternative. You can run bash scripts and do things on your own. If you only have one task to do, you should probably do that. It's a lot easier. But the problem is it'll only work until it stops working. So whether it's an encoding problem or a network problem, something's going to go wrong. And then you're going to kind of wish you had a more robust infrastructure. You could write your own, but I think that will take you more time than learning how to use BOINC. So I'll take some questions, and right before I do, I just want to thank Ekoparty and especially the translators. So let's give them a round of applause. So are there any questions?
Well, hi there, Ritter. In BOINC, No, I like in English, you know. For your BOINC application, you have to write your own integrity check for the results that the clients send you.
Only if you want to. Only if you want to.
But you run the risk of receiving, results that have been, false results.
Okay. Yes. So BOINC was initially created for volunteers. I assumed that most of you would run a project that wouldn't have volunteers. You would run it on your own computers. If you do want to do volunteers, BOINC has a lot of features for that. So there's something called homogeneous results. That says take a work unit, send it to 2 different people. When I get the results, compare them. You can do that for any number of results, so send it to 5 people. You can write your own validator to make sure that the result is the same. You can check the running time, so how long did the client run it for. And there's other options too. Like I said, you can write your own program that does any sort of complicated check that you want. So if you're working with volunteers and you're concerned about a volunteer being malicious and sending either false data, bad data, or corrupted data to try and crash you, you can build a validator that will check for that.
Otra pregunta.
Have you made any estimations about using this infrastructure? Which would be the infrastructure needed to break 1024 key in a, let's say, reasonable time, 6 months, something like that, using this?
Okay, so the question was, sorry, I didn't repeat the other one. The question was about how much work would it take to break a 1024-bit key. So breaking a 1024-bit key is more than a matter of just CPU time. You need better tools. So if I go back far enough, you'll see that the amount of work it took to break a 1024-bit key was actually much more, like exponentially more. And here we go. So the slowest part took 155 core years, 155 computers for a year. And there's an asterisk there because they didn't use Lancos. They used something else, even more complicated, called Wildeman, or Wildeman. I'm not quite sure on the pronunciation. That algorithm, again, takes about a PhD in math to understand, and the tool that does it isn't public. You have to be like a reasonable researcher at a university, then you have to email a guy and like ask him if he'd consider it, sending it to you. So I don't want to discourage anyone, but breaking a 1024-bit key is a little bit out of reach for the general hobbyist. If you are really, really, really interested, like say you flew all the way from Washington, D.C. to this talk and you're kind of curious about breaking 1024-bit, I would encourage you to hire a couple of math and computer science PhDs for a couple of years. Give them, I don't know, probably won't cost you that much, like $1 million US or something. And then you could probably get within reach of breaking 1024-bit. And if you're curious about factoring more, take a look at the materials on GitHub about the general number field sieve, and go to mersenforum.com, which is .org. Just search for Mersen Forum, and that's a community of people who do factoring for both general semi-primes, but also special numbers. There's another thing called the special number field sieve for slightly different primes, and those are much larger and much more within reach for factoring.
Hi. In the BOINC file, I see that you are using a CUDA for GPU using the password cracking. Many of us, we are using graphic CPU for cracking password, and I see that you are using the CUDA for the BOINC client. These clients are multi-platform, are only specific for some kind of operation system, or you can run in Windows, for example, in the case of CUDA with NVIDIA cards.
So the question was about how do graphics cards work on all platforms?
The BOINC client,
yes,
is that using CUDA, they are available for any operating system?
Absolutely. The BOINC client will run graphics card programs on any platform that the graphics card software will run in, period. So if you can run your application on that operating system, you can run it in BOINC. And not just CUDA, but specifically certain versions of CUDA or API cards. There's more GPU targets than I listed here. So as long as your program runs on the system, it'll run in BOINC.
Yes, another question.
Hello. Yeah, I have a question regarding this. You mentioned that, well, the linear algebra is slow and unparalleled. And I was wondering, what about a company, a large company such as Google? They have, I don't know, like thousands of computers. Can they pull it off? I mean, can they actually bring 1024 key?
I wouldn't say that they can break 1024-bit, but they can do the linear algebra better. So the going back to the slide again, the Lott-Wildeman that I mentioned, this job ran on more than one computer. The problem for us is the way the algorithm works. You need extremely high throughput. You basically need access to the memory of other computers. And that requires much more bandwidth than EC2 can handle. So if you were in a data center with tons of computers all connected by fiber, then you can run it on more than one computer. But again, that takes a special program that isn't publicly available.
Pueden preguntar en español también porque tienen mejores. ¿Sí? Bueno, si no hay más preguntas, muchas gracias, Tom.